Hi, guys. How's it going? Just trying to let everybody in the meeting here. How you guys all doing today?
Good, how are you?
Good, thank you. All right, so just as a recap, some stuff that we have today, we've got our quiz 5354, 4.6, and 4.5. Okay. Also, I wanted to mention a student in my other class asked me about give me a sec. The homework in chapter 5.4. You guys can skip questions 33 and 34. One of them is like writing an essay. You can skip that. The other one is doing a proof. Don't sweat that one either. So you can skip those two questions. I won't take off any points if you don't do them. So don't forget our quiz. The homework for these three different areas are going to be due tonight at midnight. Okay. And then today we're going to wrap up. We basically only have like one example to go through on chapter 4.6. So we're going to go through that one example on 4.6 and do the endpoint check on it. Excuse me. And then basically I'm going to leave it open for you to ask me questions. You can think of this as like a review session. I did not want to start chapter 3.1 today because it's such a different topic than what we're doing. And I really wanted to make sure that you guys got the ideas and everything. You were solid in all of the series stuff. Okay. So make sure if you have any questions, you know, you can think about today is a good time to ask them. So administratively also, our quiz will open up at 3 o'clock today. You're free to start at any time between today at 3 o'clock. And I would say don't start it any later than say 2 o'clock tomorrow so that you have time to take it, upload it, and, you know, kind of have it submitted. So just keep that in mind. Okay, so save your questions for a few more minutes because I'm going to work through the chapter 4.6 question and then you can ask questions. Okay. Yeah. All right, so 4.6. So this is lecture examples for 4.6. Okay. I thought we actually were going to have a lot more lecture examples to work through, but as it turns out, hang on a sec. As it turns out, a lot of the other stuff, the other lecture examples aren't things that we were checking radius of convergence on. So we're not going to do, we don't need to do all the rest of those. Okay. So example number 3 was that we needed to find a power series for this particular function, right? So we did it through integration, and then we came up with this right here is our power series, okay? So the sum -1 to n, x minus 1, right, n plus 1. So we have an initial condition, sorry, we did that already. Our ratio test, okay, I guess we did that offline. Our ratio test showed that we had a radius of equal to 1, and our center is at x equals 1, which makes our interval of convergence center plus or minus radius. That becomes 1 minus 1 and 1 plus 1. So we're going to go from 0 to 2 on our endpoint check, and we need to figure out based on our endpoint check, right, are we going to include these numbers or not? Okay, so let's go ahead and start with our endpoint check here. So the endpoint check basically says we're going to take our series right here. Okay, we're going to take our power series and we're going to plug in x equals 0 and evaluate it as a series and see if that series itself is going to converge. If it does, we're going to include it in the bounds, and if it doesn't, if it diverges, then we're not going to include it in the bounds of our endpoint. So this is chapter 4.6, example 3. This is our endpoint check. So in no particular order, we'll do x equals 0 first. Okay, it doesn't matter which one you start with. X equals 0. Everywhere I see an x in my power series, I'm going to substitute in 0. -1 to the n, 0, -1 to the n plus 1, all over n plus 1. Okay, so what do we get when we simplify this out? This is going to be n equals 0, -1 to the n. I'm going to get, this is -1 to the n plus 1, all over n plus 1. Okay, So when we do this, yeah, I was right. Okay. Sorry. So when we do this, this is like saying n equals 0, minus 1 to the n from before. I have minus 1 to the n from here times a minus 1 all over n plus 1. Okay, these cancel each other. Okay, negative times negative. So what I'm left with is minus 1 all over n plus 1. Okay, so what I'm going to do is I'm going to do a limit comparison. I'll do a comparison. Do limit comparison with it's going to be negative 1 all over n, which is a negative p series. P equals 1, so therefore it diverges. Okay, so if I do a limit comparison on this limit, sorry, let me scroll up. So limit as n goes to infinity, I'm going to go minus 1 over n plus 1, the series I'm given, all over minus 1 all over n. And this is going to become n. The negatives cancel. I'm going to be left with n all over n plus 1. Okay, this thing here goes to 1, n goes to infinity, which is a positive finite number. So both series have the same behavior, which means that we're going to say both series diverge. I compared it to a divergent p series. I have a positive finite number, both series diverge. Okay, that means 0 is not included in my interval. Okay, that's our first endpoint check. Our second endpoint check is doing the same thing but with x equals 2. I'll draw a line here. X equals 2. You can go sum n equals 0 to infinity minus 1. So I'm going to plug in everywhere I see an x, I'm going to plug in a 2 n plus 1 all over n plus 1. Whoops, and I'm sorry, there's an n there. Okay, so now let me scroll this up a little bit. So now what happens is, right, let's simplify this. Minus 1 to the n. This is 2 minus 1. This is just 1 to the n plus 1 all over n plus 1. So what we get here, minus 1 to the n all over n plus 1. This is an alternating series. So I'm going to do an alternating series test. I take the limit. I take the limit as n goes to infinity of 1 over n plus 1. This thing goes to 0. My second check is n plus 1 plus 1 is less than or equal to 1 over n plus 1. Great, so this thing converges. So if it converges, then that means my interval is going to contain the bounds too. So we would conclude, I'll just write it down here in the corner, my interval is going to equal to 0 to 2. 0 is not included, 2 is, based on our convergence. Okay. See if I can get both endpoint checks on the screen here. How's that? All right, so that's 4.6. Okay, that was the last example. I suppose I could have done it yesterday, but it seemed like we covered a lot of ground yesterday. So 4.6, I'll scan in. I'm scanning in right now the examples for 4.5. And I'm scanning in, after this, I'll scan in the example for 4.6 as well. At by sometime tonight, I'll post that to our Canvas page. Okay, so what I'd like to do at this point is I can open up to questions. If you guys want to ask questions on homework problems or whatever, we can go 5.4, 5.3, 4.5, 4.6. If you want to ask questions on any of those, I'm totally open to it. Or if you can go back to other chapter sections, 5.2 or whatever, although our quiz today is on 5.3, 5.4, 4.5, and 4.6. 5.4, number 9. Okay, all right. Okay, guys, I'll have this here. I'm gonna take it away. Okay. Okay. So give me a sec. Okay, so let's just go in order. So 5.4 number 9, we'll do that one first. I'm just looking at the chat. So if you guys want to say it into the chat, I'll just go in order as I see things there. So 5.4 number 9. Yeah, this is an interesting one. So we were just talking about this in office hours. I think, oops. Okay. There are a couple of things that we can do here. I think that it's probably going to be best. This is what we were talking about in office hours, and I think I convinced myself that if we can show, we can do a couple of things. So watch this. If I show, so my first method would be an alternating series test to show conditional convergence, right? That we know if it would converge, it does actually. But and then after that, I would have to show absolute convergence, because I think they were asking about absolute convergence here. So I have to show absolute convergence, and then so for that I would have to do something else. Like I think I did a limit comparison test, which is going to show convergence. I think our best method, right? So these two go together. Our best method, actually, we did this in office hours, was just showing with the ratio test, because the ratio test is a test for absolute convergence. If it converges with the absolute value, then it's going to converge without it. So if we can show that it converges with the ratio test, then I'm kind of like one and done, right? So let's try it with the ratio test. So I'm going to go the limit as k goes to infinity. This -1 to the k goes away with the ratio, with the absolute values. So I'm just going to go 1 over 3 to the k plus 1 factorial plus 4 all over 1 over factorial plus 4 there. So let's clean these up, right? So this is going to end up looking like 3k factorial plus 4 radical all over. Okay, and there's an absolute value there. So what's going to happen is, as it gets bigger, the 4s are not going to contribute as much, right? And these 3s, the radical 3s, right, they become, they can cancel them out. So the radical 3s go away, the 4s don't contribute as much. So we're basically looking at, as k gets bigger and bigger and bigger, radical k factorial all over k plus 1 factorial, which means that I can actually, this is going to go down to, oops, let me write it over here. K goes to infinity. This is going to end up being more like 1 over radical k plus 1. Okay, because of how the factorials are going to clean up. So because of this, this is going to go to 0, which is less than 1, which means it converges. And I'll say it converges absolutely. And then I'm done. So I've saved myself a whole bunch of time. The only problem that you might have with something like this is if you try jumping right ahead to it and it's inconclusive, and then you're going to be like, uh-oh, now what? So then you have to go back and kind of check it individually, and then maybe try some other tests, like actually take away the absolute value and take away the negative by taking the absolute value, and then trying some other, maybe a comparison test. But if the ratio test works on your first try, which it does here, if we can show convergence, then we're showing absolute convergence. And so I think we're good. I mean, and I know this one does converge. This will work too, but there's an awful lot more work. Like there's the work for the series test here. And then I have to do, whenever I do a limit comparison or a direct comparison, the thing that I'm comparing it to, I have to show whether that converges or diverges. And then what I compare this to, I compared it to 1 over k factorial. And then I did the ratio test on that. Well, then I'm like, well, why didn't I just do the ratio test in the first place? Because I had to show that this was going to converge. So I thought, let me just do the ratio test from the first case. So I think this is your best bet on 5.4 number 9. It looks like, I think Harrison, you meant, did you say 5.4 number 13? I think it looks like. All right, I'll start with that one. 5.4 number 13. 13. Okay, good. Yeah. So this one is good too. 5.4 number 13. All right, so this one is cosine of k pi over 2 all over radical k. So let's just enumerate out some of these terms here with the cosine, right? So k is an integer. So depending on, we can't start at 0, but we'll start at 1. So cosine of 1 pi over 2. So cosine of pi over 2 is equal to 0, right? Cosine of 2 pi over 2 is equal to cosine of pi, which is minus 1. Cosine of 3 pi over 2, which is equal to 0. Cosine of 4 pi over 2, which is equal to cosine of 2 pi, which is equal to cosine of 0. This is equal to 1. And then, you know, basically we're going around the unit circle, right? So we're just going to be looping our values 0, minus 1, 0, positive 1. So, but because of the zeros here, it looks like the even k's. So when k is even, we actually have like an alternating series test. So I'm going to go k is even, like say for example, this is going to be like minus 1, let's say k plus 1, because if it's always even, this won't be alternating series anymore. So I'll do k plus 1 all over radical k. So really what we're dealing with here is a glorified alternating series. But we had to prove it to ourselves to take a look at. So I'm going to do the alternating series test, which is my first test, the limit as k goes to infinity, 1 over radical k is equal to 0. The second criteria is 1 over k plus 1 radical k, so that converges by alternating series test. Now they're asking us to check for absolute convergence, I think. So I'm going to take this and I'm going to go like that. And what am I going to get? I'm going to get 1 over, which is 1 over k to the 1/2, which is a p series. My p is equal to 1/2, which is less than 1. Therefore, this thing diverges. So if it only converges when it's an alternating series, but it diverges otherwise, that means that it converges conditionally. Okay. Okay, so I'm just going down the list here. So 5.3, number 13. Okay. Okay, you guys all have this here before I turn the page. Well, I'll give you another second to write. Okay. All right. So 5.3, number 13. So 5.3, number 13. So they say we're given a series. Find a second series, which is a p series or geometric series to compare by a comparison test. Okay, so question number 13. So this looks like p equals 4 to infinity, p plus 1 all over 0.9 to the p. So really the dominant term is our exponential. So I'm going to be taking a look at 1 over 0.9 to the p, right? Which I'm going to compare with that, which is essentially this is 1 over 0.9, which is really 10 over 9 raised to the p power, right? So just because this is 1 over 9 over 10, so this becomes 10 over 9, which is a geometric series. Okay, geometric series with our r is equal to 10 over 9. So our issue is that our absolute value of r is greater than 1. So therefore this thing diverges. Okay, this here, our geometric series is smaller than p plus 1. So this also diverges. And we'll say by direct comparison. test. Okay, Kobe, I'm just going to do one of them and then we can come back to the other one. Just remind me if I forget number 21. 5.4, number 15. All right, so this one is this is what we're given. So when we first start off, this is an alternating series. You do the alternating series test. So I'm going to check, so the limit as k goes to infinity. This thing goes to 0 because the k over 6 is bigger in the denominator, so that goes to 0. I won't write it all the way out, but a sub n plus 1 is just then a sub n. So this thing converges. Okay. All right. So now we have to do the absolute check. Right. So I take the absolute value of my series, right, which is going to give me okay, so now I'm going to take a look at my highest degree terms, k cubed, oops, sorry, 3/2 all over k to the 6/2. Okay, so this is like 1 over k to the 3/2, how it translates down to. So I'm going to do a limit comparison with 1 over k to the 3/2. This right here is a p series with p equals 3/2, right? So which is greater than 1, so it converges. Okay. Right? Okay, so let's do it. So I say the limit as k goes to infinity. Always these absolute convergence checks are a lot of work. I'm going to take my known series here, which is k cubed plus 1, k6 plus 1, all over 1 over k to the 3/2. So this becomes times k to the 3/2. So remember, this reduced as k got really big. This reduced to 1 over k to the 3/2. So my ratio is equal to 1. There's no number out front, which is positive and finite. Therefore, both series have the same behavior. So both series converge. So it converged as an alternating series, and now it converged after we took the absolute value. So I can say this thing converges absolutely. Okay. 42. Okay, so 42 on 5.4. You guys will have this. I'll give you a minute to finish writing it. Looks like a nice day out.
Yeah, it's pretty nice.
Okay, so we're going to do a number 42 on 5.4. All right, so we're given a power series, k equals 1 to infinity, minus 1, k plus 1, x to the k all over k cube root. Okay, so we need to figure out what's the radius and center and interval. So the first thing I have to do is do the ratio test to figure out my radius of convergence. So limit as k goes to infinity, x to the k plus 1 all over k plus 1 cube root all over x to the k, oops, sorry, that's a k cube root, and that's in the absolute value, so that gets rid of the -1. So let's clean this up and put things together. So this goes x to the k plus 1 all over x to the k. This becomes k cube root all over k plus 1 cube root, okay, which is equal to, this becomes x times like that, okay? So, these have the same highest degree term as k goes to infinity, so they drop out to their ratio, so this goes to 1. This is the ratio test and a power series. We want it to converge, so it has to be less than 1. So what I'm going to say is absolute value of x is less than 1 to converge. This here is my radius. So I'll start summarizing. My radius is equal to 1. Our center, right, this is where it's centered. Center is equal to 0. So our interval is equal to -1 to +1. Now I have to do an endpoint check to figure out if those are included or not. All right, so let's check. We'll do it. Let's write it down. So endpoint check. Okay, I'm going to scroll up a little bit here. So x equals 1. Doesn't matter what order you do them in. So I'm going to look at my series k equals 1 to infinity -1 to the k plus 1. Everywhere I see an x, I plug in a 1. Okay, which looks like okay, which is an alternating series. Okay, so we're going to do our alternating series test. So the limit as k goes to infinity, 1 over k to the 1/3 equals 0. Good. The second test, 1 over k plus 1 cube root, 1 over k cube root, and that's true. So this thing converges. So it looks like +1 is included in my interval. Now, my other endpoint, x equals -1. Everywhere I see an x, I plug in a -1. K equals 1 to infinity, -1 to the k plus 1, -1 to the k, all over k here. So let's do something with all this here. So this is like -1 to the k times a -1 time, that comes, I just broke this apart, times a -1 to the k, all over k. I'm going to write it as 1/3. So these cancel, and I'm left with -1 all over k to the 1/3. So this is just a constant -1 times a p series. Okay, the p is equal to 1/3, which is less than 1, so this thing diverges, right? Which means -1's not included in my interval. Okay. 5.3, number 40. Oh yeah, number 40. This is a weird one. 5.3, number 40 is like, I think it's using an identity. It's kind of like you have to be in the know. It's a trick question, so don't sweat it if it doesn't look obvious like what you're supposed to do. So we're given p factorial p squared all over p to the p. Okay, so we're going to do a root test. If we do a root test on it, right, we're going to get the limit as p goes to infinity. The pth root, I can take the absolute value, right? So this is going to end up being, let's see, the pth root of p factorial p squared all over p. Okay, here's the trick, which if you're not in the know, it's going to be very frustrating. This is equal to 1 over e, okay, which is less than 1, which therefore converges. Don't worry if you didn't understand, if you didn't know that. Um, 5.4, number 5. so 5.4, number 5. Five goes, hang on a sec. Okay, so if, this looks like p equals 4 to infinity 7 plus p to the 1/7 all over p to the 8/7. So I'm going to break this up into two pieces. 7 p to the 8/7 plus p to the 1/7 all over p to the 8/7. So here, this is a p series. P is equal to 8/7, which is greater than 1, so it converges, right? Here, right, this one is, this is a p series, right? If we clean this up, right, this is equal to 1/7 minus 8/7 is 7/7, or 1/7. So then basically we're looking at, is that right? That's -1, so that's 1 over p. So I think this becomes,
Professor,
yeah.
I think that's the wrong problem.
Oh, really? I'm looking at, did they say number 5? 5.3? Oh, I do it. Well, okay, well, that explains why you guys are wondering.
Well, I will say I was about to ask for this one. I was stuck on it a few minutes ago, so if you will finish it, I would appreciate it.
Okay, great, let's do it, all right? So then this is equal to the sum 1 over p, right? So 1/7 minus 8/7 becomes minus 7/7, which is 1 over p. So the p series, p is equal to 1, which means it diverges. So then the whole thing, whole series diverges. Doesn't matter if one part converges, if the other part diverges, then the whole thing's going to diverge. Okay, so that's number 5 on 5.3. Sorry about that. So this is 5.3. My bad. Well, now I know you guys were paying attention, right? Sorry. Okay. All right. Okay, so 5.4, number 5, right? Was that 5.4 number 5? Okay. So this one we have the sum -1 to the k, 1 plus 4 over k here. All right, so we have an alternating series because I've got this, right? So this is an alternating series test. So I'm going to say the limit as k goes to infinity, 1 plus 4 over k, right? Which is equal to, this goes to 0, this is equal to 1. Oops, which is not equal to 0. So it bombs out of my alternating series. But that also means I can do my nth term test, which is the limit. I'll write it all the way out again, which is not equal to 0. That is this equal to 1, which is not equal to 0. Therefore, this diverges. Be careful. The alternating series test doesn't tell you divergence. It only tells you convergence, even though that first test on the alternating series test is essentially the nth term test, right? So if it fails this one, that's passing the nth term test. Okay. So it looks like you guys crashed.
Yeah, we just the Zoom like rebooted.
That's weird because it didn't like ask me. Looks like a couple people got booted off, but
It might be a location-based thing. If the people, like I'm in West, so if the people who crashed are also on this side of campus, that might have been it.
okay,
No, I'm on the other side of campus.
that's interesting. Yeah, it looks like
Yeah, I'm on Midtown. I think anyone on like school Wi-Fi probably just crashed, but if anyone's like at home or not on school Wi-Fi, then they were able to stay on.
they didn't say.
Yeah.
Yeah, also possible.
Okay, I'll leave this up. So this is 5.4, number 5. Here's 5.3, number 5, and 5.4, number 5. 5.4, number 5, it's an alternating series, but it bombs our first test. Okay, on the alternating series test. Alternating series test doesn't test for divergence, it only tests for convergence. but this leads me right into the nth term test for divergence. So I write it down again. So in case somebody who is grading the final exam wants to make sure that you, looks like you guys are having a hard time. Can you guys all hear me okay?
Yes.
Okay, I see. Okay, good. Looks like people can. Okay, good. So this
Okay.
leads right into the nth term test for divergence. You unfortunately should write it out again. Okay, in this class right now, while you're learning it, you want to write it out again to show that you know what test you're doing. Okay, as you move along in other classes, you can just go ahead and do these tests. You don't have to, you're just going to say diverge, converge, whatever. Okay, so you've done the nth term test. It's equal to 1, which is not equal to 0. Therefore, it diverges. 5.4, number 5. What do you guys think? We're just going to roll through questions. If we get to a point where you guys don't have any other questions, then we can leave early. But if you guys have questions right up to the end, we can keep going. 5.4, number 21. Okay. Let me make sure I'm in chapter 5.4 or number 21. Okay, so 21. Okay, so this one. Oh yeah, so these are interesting. So what they're saying, let me read the exact, let's see, let me bring it up. Give me just a second. I want to read the exact homework problem. Because there's a nuance here in how they've said it. So give me just a second, let me read it out loud. So 5.4, number 21, it says, show that the alternating series converges, okay, and give a partial sum, which is like the sum of the first 6 terms or the first 70 terms or the first million terms. Give a partial sum which estimates the entire sum to within plus or minus 0.01. Okay, so what we need to remember is our remainder is equal to 0.01. That's what they're telling us that they want us to do. Okay, so if they're giving us this remainder here and they want us to use that, so then that means that, let me write down the question here. So this is k equals 1 to infinity minus 1 to the k minus 1, 1 over radical k. Okay, so what they want us to do, first off, we have to show that this is going to converge, because if it doesn't converge, then there's no point in trying to figure out a sum. So let's check. This is an alternating series. So I'm going to do the alternating series test. So I'm going to go the limit as k goes to infinity, 1 over radical k, that's equal to 0. My next check, 1 over k plus 1, radical is less than 1 over k radical. Yep, so this converges by our alternating series test. Okay, so if it doesn't converge, there's no sum, right, to calculate. It's just, it would be infinite. So now what we need to do is to come up, approximate the sum with a partial sum. So remember our partial sum, let's remember, so if I go just as an example, S sub 3, our partial sum is a sub 1 plus a sub 2 plus a sub 3, okay? And then I've got plus my remainder. Okay, so we approximate the remainder with our a sub 4 term. So we're gonna approximate the remainder with the next term up that we would have had, right, after we finished with our partial sum, okay? So now the question is, they're giving us the remainder. They're telling us this a4 term, or a sub n term, is equal to 0.01. So I have to figure out what's the k value that's going to make that work. So I know that I'm dealing with 1 over radical k, and I want that to be equal to 0.1. I know this is plus or minus, right? There's an alternation happening here, but I just need to know the absolute k value that's going to equal to 0.01. That's going to give me that. So when I do this, right, I'm going to cross multiply. So I'm going to get square root of k is equal to 100, right? I square it, so k equals 10,000. So this is the K value. So A sub 10,000 is going to equal 0.01. Okay, so that means that my partial sum is equal to S sub 9,999 because it's the one just below that, right? And there's no way I'm gonna do this without a computer program, but I can say K equals 1 to 9,999. There, and then that's my partial sum. That's totally fine to write it like this. You're not expected to come up with a number when it's this big. Even on any of these, I think number 22, you need to do the same thing. Like so for number 22, you're going to get, I got K equals 10. So in theory, I could sum through and sum up the first, 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, right? And come up with a number, but I don't need to. I'm just going to write it as a summation. So 5.3, 27. All right, so these say find a p-series, a geometric series to do limit comparison, a limit comparison test. Okay, so number 27. 27 we're given, sorry, let's make this straight for you. So number 27 we're given K equals 1 to infinity, 3 plus cube root of K all over 7 plus the square root of K, right? This is the square root of K. So what we're dealing with is I need to find something. So I'm going to compare my highest degree terms. So I'm going to go K to the 1/3, K to the 1/2. So this is 1/3 minus 1/2, right? So this is going to be like comparing it to 1 over K to the 1/6, okay? Which is a P series. P is equal to 1/6, which is less than 1, so this thing diverges. Okay, it's a divergent P series. So now I'm going to do a limit comparison to see if this one's going to diverge, right? Because I'm going to compare it to a divergent P series. So if I get a positive finite number, this is also going to diverge. If this is inconclusive, I got to do maybe direct comparison test. All right, so limit K goes to infinity, 3 plus 7 plus, right, all over 1 over K to the 1/6. Right, so this is essentially, right, we're looking at this reduces down to 1 as K gets really big. The 3 and the 7 drop off in terms of impact on our values. This reduces down to 1 over K to the 1/6 times K to the 1/6. Basically, we're dealing with this as +1, which is a positive finite number. Therefore, both series diverge. Okay, Jill, I'm gonna go down to next people asking questions and then remind me if I forget to come back to 42, remind me, I'll come back to it, okay? Just to be fair. So 5.3, number 35. Okay, so this one, 5.3, number 35. So 5.3, number 35 looks like m equals 1 to infinity, 4 all over 0.9 to the m times m squared. So I've got this number to the m, okay? So I'm going to try a root test. Okay, so I'm going to go limit as m goes to infinity. This is going to be the mth root. I have to take the absolute value, although, I'm pretty confident these are going to be positive. 0.9 to the m squared. Okay, so this is my root test. So this is equal to, this is 4 mth root, which is 0.9 times m to the 2 over m. So as m goes to infinity, right, this here, it looks like it's going to be, this is 2 over infinity, so this is to the 0. So this is like infinity to the 0. It's our indeterminate form. But basically, what happens is we're dealing with this number here is going to win out. So this is 1 over 9 over 10, which becomes 10 over 9, okay, which is greater than 1. So therefore this thing diverges. Okay. So I'm going to say this thing goes to 1. And then this dominates. And looking for number 10. Okay, so 5.4, number 10. So this is minus 1 to the k, ln of k. Okay, so I'm going to do an alternating series test. Okay, so because it's an alternating series, so I'm going to take the limit as as n goes to infinity. 1 over k ln of k. This thing goes to 0. Let's see. So 1 over k plus 1 ln k plus 1. 1 over k ln of k. Check. So this thing converges. Okay. Now I have to do the absolute check, right? So this becomes which I can do the integral test on. All right, so if I do the integral test on this, what this is going to become is 1 to infinity, 1 over x ln of x. And I can do that because, right, it looks like a function and then the derivative's in there already, right? So my u is ln of x, my du is 1 over x dx. So I've got this, technically I need to convert this first. Let me do b 1 to b. This is going to be 1 over u du. So then we're going to get ln of u, right? So then let's substitute back. I'm not putting the bounds on at this point because I know we're going to substitute back and I'm not worried about it, but I know there's some colleagues who get very particular about it when they grade the final exam, because this is the bounds for x, so I'm not going to rewrite the bounds for u, so I'm just going to leave them off until I'm done substituting back. So then I'm going to substitute it back. So it's going to look like the natural log of x. I know we have this natural log here doesn't have an absolute value on it, but we have it on the outside because we're taking the natural log here. So this is the natural log of x, and we're going to go from 1 to b. Oops, and I should write it back in. My limit as b goes to infinity. So let me rewrite this to make it look prettier. Okay, so let's evaluate that. Limit as b goes to infinity. Natural log of b minus the natural log of 1. Okay, it doesn't matter that this goes to 0 because this one's going to infinity. So then this diverges. Because the limit doesn't exist, the series diverges. Right, so you can see what I'm writing. So therefore, we're going to say that our series converges conditionally. Because it's conditional on it being an alternating series. Okay. Back 5.3, number 42. Okay. I'll let you guys finish writing that. Then we'll go back to 5.3, number 42. Okay. You guys okay with this one? Okay, so 5.3, number 42 looks like m equals 1 to infinity, 7 plus a minus 1 to the m m plus m to the 1/2. Okay, so I'm looking for upper and lower bounds. All right, so what I'm going to do is, because I've got this plus or minus 1, so I've got the sum 7 minus 1 m plus m to the 1/2 is less than or equal to my, I'm going to call this b sub n. Which is less than or equal to 7 plus 1 m plus radical m. Okay, so what we're looking at is 6 to the 1/2, which is less than or equal to 8. Oops, that's a sum to the 1/2. Okay, so what I'm going to do is I'm going to do a comparison. Compare with 6 over m, okay, which is a divergent p-series. It's 6 times a divergent p-series. P is equal to 1, which is why it diverges. And so what I can do is I can do a limit comparison. And I only need to show this one's going to diverge, because if it's going to diverge, right, then that means the other one's going to diverge too. So if I do a limit comparison with this, then what I'll say is the limit as m goes to infinity of this thing here, 6 m plus m to the 1/2 all over 6 over m, which becomes m over 6. So as m gets really big, right, these things dominate, and I've got 6 over 6, so that's equal to 1, which is positive finite. So therefore both series diverge. This is my lower bound, right? So we just showed that the lower bound diverges. Lower bound diverges. Therefore, our series b sub n also diverges. That's a lot of work, right? 0.6, number 16. Sure. Give me a sec. Oh, yeah, I think, did we, so we, let me think about this one. I think number 16 has a point convergence, it looks like. So let me scroll up a little bit. So 4.6, number 16, which is, this is also going to be true on P of X too. So when we did P of X, right, we used our ratio, I won't go through it again, but the ratio test on here showed us that our radius was equal to 0, which means that we're dealing with a point convergence at the center. So if you just have a point convergence at the center, then there are no endpoints to check. So you're kind of off the hook. You don't have to worry about 16 on 4.5 or 4.6 because there are no endpoints to check. Number 16. Oops. What do you guys think? I'm hoping, you know, going over all these problems, I'm hoping it's sinking in. We've spent a lot of time on it because I think it's important. It makes up a huge portion of like what we're trying to do. You know, chapter 4 and chapter 5 are like more than a third of the semester in terms of what we're trying to cover in the class. And so I'm hoping that, you know, spending time on it helps you understand, and I hope it's becoming more clear. 5.3, number 19. Okay. All right, let's see. Okay. So 5.3, number 19. Okay, so 5.3, number 19. So we've got k equals 1 to infinity, 2 plus a minus 1. This is kind of like the one that we just did. k to the 1.1. So we've got our 2 plus or minus 1. So this is going to end up being in a lower bound and an upper bound. So I'm going to have a series that goes to minus 1 k to the 1.1, which is less than or equal to our series. I'll call this b sub n here, which is less than or equal to 2 plus 1 k to the 1.1. Okay, so this is going to be 2 minus 1. This is 1 over k to the 1.1. This is 3 all over k to the 1.1. So these are just, this is a p series, right? And then this is a multiplier of a p series, right? It's 3 times a p series. So our p is equal to 1.1, which is greater than 1, which means it's going to converge. This also converges. It's the same thing, right? P equals 1.1. They both converge, right? Which means that our inner series must converge. Therefore, b sub n also converges, sorry. Also converges. What do you guys think? I'll post the videos later today. Good, I'm glad it was helpful. I'll post the videos later today as soon as I get them. Sometimes it takes a while from the cloud. And then you'll have this as a reference in case I went fast, you know, trying to go through this stuff. You'll be able to pause the video and take a look at it. Okay. If you guys have any other questions, I can answer them or we can leave early. It's totally up to you. Don't forget the quiz opens up today at 3 o'clock. And the homework is all due tonight by midnight.
Thank you.
Okay, thanks guys. See the direct compare. Can you use a direct comparison test for series which have all negative terms?
Thank you.
Just that the terms asymptote to y equals 0. One negative series diverges in the less one than another series for all n, and the other series also diverges. So you mean like they diverge to negative infinity or something? So it's kind of, I think what happens is if you've got like a negative, like let's say you've got like a negative 1 over p, right? So this is a p series that's going to diverge, right? But it's a negative. We kind of think about it as negative 1 times 1 over p. So what we're going to do is we do the p series. P equals 1, this is diverges. And it's a multiplier, constant multiplier times an existent p series, say for example, right? And so then this constant multiplier doesn't change the fact that it diverges, right? And so that's how we would think about it. And I think probably the same thing would be true if we did, if this was like negative 1 over p squared, then this would become minus 1 times 1 over p squared, which p equals 2. This thing converges, right? This is a convergent p series, right? And I think it's just a negative multiplier on a convergent p series. It doesn't, so I think I'm not trying to understand your question. So can you use the direct comparison test for series which have all negative terms? Well, if they asymptote, then if they asymptote to y equals 0, then that kind of implies that there's a convergence. I think if it asymptotes to y equals 0, that implies that it's gonna, I guess they asymptote to y equals 0, but then, wait, so they're coming up. Well, wait, so if they're all negative terms and they asymptote at y equals 0, I'm having a hard time picturing it, but I think you would still be sandwiching it between, I'm gonna do a comparison test, like whatever my series is, I'm gonna try to compare it to something that I know, right? So regardless of what's happening, and then I'll wanna show, is this one greater or less than what I'm trying to do, right? And so it's just a multiplier on something. And then I can just say, okay, it's a multiplier. And then when I do the comparison test, whether it's a limit comparison or a direct comparison, it's almost like the multiplier goes away and I'm just looking at this individual series. It does help to pull out the multiplier so that you can visualize it better. Okay, you guys good? All right. Okay, guys. All right. Like I said, I'll post the videos as soon as I get them so that you can have them. And the quiz opens up at 3 today, so make sure you're checking that out. And don't forget to pass things in tonight, so that by midnight tonight, so that you can do that. And like I said before, I do accept late homeworks, but it just kind of falls into the to be graded later file, as opposed to being graded when I grade the whole batch. So if you do it, submit it after I grade the class, then I will grade it by the end of the semester, but it may take a while, just to let you know, because I don't know why it takes so long to grade when things are online. You think it would be more optimal, but it's not. Okay. All right, you guys. Well, if there are no more questions, then I hope you have a great weekend and enjoy the nice weather, but also study. Okay. All right. Take it easy, guys.